Hey, Mr. Yeller here back in the wood shop, continuing Module 14 with Lesson 3. Alright, Lesson 3 is talking about thermochemical equations. And our focus question is, why do we include energy changes in chemical equations? Now, we don't do this all the time, but sometimes it is very handy. Here are some brief vocab for you before we get going, so go ahead and pause, write down your vocab so you can define it throughout the lesson. Review vocab. Combustion reactions. A combustion reaction occurs when a substance reacts with oxygen and it gives off energy, usually in the form of heat and light. Okay, you are very familiar with combustion reactions. That's when you're burning stuff. Okay, many combustion reactions also create CO2 and H2O. So a thermochemical equation is an equation, it's a balanced chemical equation that includes the physical states, so solid, liquid, gas, or aqueous, of all the reactants and products. So we got a balanced chemical equation including the physical states of each reactant and product and the energy change. And that last part is what makes it a thermochemical equation. And the energy change is usually expressed in the form of delta H, which we talked about in Lesson 2. And so here's an example. We got hydrogen gas reacting with oxygen gas to form water, and our delta H follows the equation with a delta H of combustion equal to negative 572 kilojoules. So this would be a thermochemical equation. Alright, so enthalpy of combustion, so delta H of combustion, you can see the little COMB down there meaning combustion, is a complete burning of 1 mole of that substance. So for example, we got glucose here, C6H12O6. We're going to combust it, so react it with oxygen, so we end up with CO2 and water. And that is a combustion reaction, so we have a delta H of combustion equal to negative 2,808 kilojoules per mole. So we know that that's the heat of combustion for that reaction. All right, standard enthalpy changes are given delta H with this superscript 0. That means that they were measured for the substances under standard conditions. So standard conditions are basically like under normal, usual, everyday conditions, what form or what state would that element or molecule compound be in. Okay, so oxygen is normally a gas, hydrogen is normally a gas, water, H2O, would be a liquid, so on and so forth. Okay, so here's some standards. Standard enthalpy of combustion for some molecules. We got methane, propane, sucrose, see glucose in there. All right, and notice that their states are their standard states. All right, go ahead and pause the video, read through this question, and see if you can set it up and solve it. And we will be back with the solution in just a moment. So pause in 3, 2, 1, pause. Okay, and we're back with the solution. So we were given mass of glucose, 54 grams of glucose, and we know the heat of combustion is negative 2,808 kilojoules. So that should be actually kilojoules per mole, would be the molar heat of combustion for that. And we want Q. We want to know how much energy was transferred. So we need to first convert our glucose to moles so that we can use it with the heat of combustion. So in order to do that, we need to multiply our mass. We need to divide our mass by molar mass. We've learned that trick before back in ideal gas laws. So mass divided by molar mass gives us the number of moles. We take that number of moles and we're going to multiply it by our heat of combustion. And we see that the moles cancel out. So if we think of heat of combustion as kilojoules per mole, so 0.3 divided by 1 mole, 0.3 moles cancels out with moles down here, and we're left with kilojoules. So looks like we dropped a negative sign somewhere. So anyway, this would be 842 kilojoules of energy that would be released in that reaction. So 842 kilojoules that that was in, they're using the term evolved in the reaction. So 842 kilojoules were transferred out of this reaction into the water of the bomb calorimeter. All right, go ahead and pause the video and you try this one. So pause in 3, 2, 1, pause. Okay, back with the solution here. We need to write down what we know and need to know. So 206 grams of hydrogen were given to us. We also know the heat of combustion here. It's written right here, so I didn't rewrite it. And we want to know Q. So same thing again. We're going to take our grams. We're going to divide it by our molar mass of our molecule to get the number of moles. Number of moles is then multiplied by our heat of combustion. So we got negative 286 kilojoules per mole, and that works out to be about 2.92 times 10 to the 4th kilojoules. So why am I expressing it in kilojoules, not joules? Up here I said Q in joules or kilojoules. I kind of reserve the right to do either one of them based off of the scale of the number. This is a pretty darn big number as it is, so we're just going to stick with kilojoules here. All right, now there's another way that we can actually do this. Instead of doing it in multiple steps, we could do it all in one step. We could take our grams, convert it to moles by dividing by our molar mass, and then go ahead straight into canceling out our moles with another conversion, which is that heat of combustion, and multiply by our heat of combustion, you end up with the same answer. Okay, so you could do it in 2 steps, or you can just do it in 1 step. Okay, so moving on here, we got changes of state. So enthalpy of vaporization, or what we usually call heat of vaporization, is the amount of heat required to vaporize 1 mole of liquid. The heat of fusion is the amount of energy required to melt 1 mole of a solid, so going from a solid to a liquid. And you can see in this table here a set of heats of vaporization as well as heats of fusion for several different molecules. So here is water. Here's kind of an illustration of water. So heat of fusion is 6 kilojoules per mole of water. And then you can see that it takes 40 kilojoules to vaporize that same amount of water. Now that means that we get, or it has to release 40.7 kilojoules per mole of water in order to condense from a gas down to a liquid. And then likewise to freeze it to a solid, it has to release, that mole of water has to release 6.01 kilojoules of energy. All right, so let's go ahead and pause the video again, see if you can solve this problem on your own, and we'll be back with the solution in just a moment. And we're back with the solution. So we needed to calculate the heat required, so Q again. We were given a mass of 25.7 grams of methanol. And here I have the solution laid out all in one line. So I took my grams, divided it by molar mass again to get moles. And then I take my moles, multiply it by my heat required to melt. That's supposed to say melt, my apologies. So that would be heat of fusion. So this is the heat of fusion for methanol that I got from the table. And we get 2.586 kilojoules. All right, let's go ahead and test our knowledge here. So as always, you can pause the video if you need more time. Go ahead and read the question and answer the question. And our solution, all of the above. Number 2. Solution would be C, that superscript up there. Number 3. So positive change in enthalpy. Think back to lesson 2 on this. Positive delta H would mean that energy is going into the system. So which one do we have to put energy into? It'd be vaporizing water. And number 4. And the solution is B. All right, that concludes our lesson for lesson 3. We will see you again in lesson 4, and have a lovely day.